Hello, my name's Jenny Gales. Apologies I can't be there in person, I've had some recent surgery. I'm going to be talking about climate-controlled submarine landslides on the Antarctic continental margin. Hopefully if there are any questions at the end, my co-authors might be able to answer these, or you're welcome to send me an email, it's there at the bottom as well. Submarine landslides are the largest mass movements on Earth. They transport huge amounts of sediment to the deep ocean. They can generate ocean-crossing tsunamis, which can lead to significant loss of life. They can also damage equipment and infrastructure on the seafloor, like telecommunications cables that transport most of the world's internet. Recent studies have suggested that changes in climate could actually increase the frequency of these submarine landslides. So it's really important to understand the factors triggering and causing these submarine landslides. Antarctica is an ideal place to look at the influence of climate change on slope instability, because obviously Antarctica has gone through huge changes in climate over millions of years. So our studies focused on the eastern Ross Sea, on the continental shelf edge and the upper slope in this region here. And we uncovered a huge area of submarine landslides during a Eurofleet-funded and an Italian expedition in 2017. So our study aims to look at what the timing and the frequency of these submarine landslides are. We want to look at whether these relate to climatic changes and whether they pose a risk to southern hemisphere populations. I'm going to zoom in on this section here to show you the study site in more detail. So we're looking at the eastern Ross Sea. This is the Iselin Bank, and we're looking at the upper slope of this site. These red circles here, these show some of the core sites collected during IODP Expedition 374. And I'm going to be focused on site U1523 in this section here. So I'm going to zoom in on this section to show you the site in more detail. So at the back here you can see bathymetric data that we collected during a Eurofleet funded expedition and during an Italian expedition as well. We also collected seismic data here that you can see marked by these black lines. And you can see site U1523, the IODP core site up here as well. And everywhere you can see these white dashed lines and these red dashed lines, these indicate some of the submarine landslide scarps that we can trace more than 100 kilometres along slope. And in total, these submarine landslides cover an area about 6,000 kilometres squared, so a substantial area. To give you an idea of scale, some of these submarine landslides actually have headwalls nearly 200 metres high, so substantial features. So site U1523, we drilled this site in about 800 metres water depth, and we recovered about 130 metres of sediment at this site. Our study's based on integrating this core with downhole log data and with seismic data. We also looked at visual core analysis. We did a high resolution grain size analysis every 15 centimetres down this core. We looked at the physical properties, the chronology as well. The study is going to be focused on this section here because this is where we have our seismic data that actually crosses some of the submarine landslide scarps and also extends all the way to our core site. So looking at this section in more detail, again you can see the seismic profile here in black that crosses two of the submarine landslide scarps shown by these red stars here and extends all the way to our core site, site U1523. These white arrows just give you an indication of the direction that the sediment's being evacuated in. And again, the white dashed lines are outlining some of the submarine landslide scarps. And for scale, you can see some of the scarp heights are down here. So we've got average scarp heights of about 100 metres. So looking at the seismic profile that crosses those submarine landslide scarps, again on the right here you've got our core site, site U1523, and the seismic line then extends about 15 kilometres to the shelf edge. And this is where we cross two of the scarps, S1 that I've just showed you, and S2 down here, the second submarine landslide scarp. We also cross a third buried submarine landslide here that we call S1B. Now, what we find under each of the submarine landslide scarps is a really distinct layer of sediment that we can trace undisturbed from beneath the submarine landslides all the way to our core site. And we call these weak layers. These are the layers responsible for the failure of the slope in this area. Now, what's really unique about this study is Normally during the landsliding process, those weak layers get destroyed, but because we have such excellent preservation here, we can actually trace these all the way to the core site, and we can look at the properties of the sediments at the core site to try and understand what the environment was like, what the conditions were like when those sediments were laid down, to try and understand what caused the slope to fail here. So this is the core site. We're looking about 150 metres down core here. And you can see some of the physical properties that we measured along the top here. Things like the bulk density, the magnetic susceptibility, shear strength, porosity, and the grain size that we did every 15 centimetres. And the weak layers I've marked by these blue dashed lines here, WL1B and WL1, and I'm going to zoom in on this section to show you these weak layers in a bit more detail. The deepest weak layer we didn't actually reach during the coring process, it was too deep, but we did manage to reach these during the downhole logging stage. So what we find are that these weak layers that we find beneath each of the submarine landslides are really distinct layers of sediment. And within these sediments, that they're composed of abundant and very well preserved fine-grained diatomees. So you can see one of the weak layers here and the second one down here. They have higher porosity, they have low grain size, and they're overlain by coarser-grained diamict that you can see marked by these green packages. So much coarser, much lower porosity, much higher shear strength sediments. Looking to give you an idea of the chronology, we were able to get an estimate of the ages of the submarine landslides and the ages of the weak layers by integrating the seismic data with the core data. And colleagues of mine looked at the chronology, so they looked at the datum stratigraphy, they looked at the paleomagnetic measurements to try and get an estimate of the ages of these weak layers and the ages of the submarine landslides. So what we find are these weak layers beneath each of the submarine landslides that are formed of really distinct packages of sediment. And within these weak layers, we find subtropical to temperate foraminifera species. Now, based on the chronology, the timing of these weak layers correspond to warmer than present climates. So this suggests that these weak layers were laid down when temperatures were warmer, when there was reduced sea ice, high global sea levels, and more open marine conditions. So we roughly date the ages of the weak layers to notably warm climate intervals. So weak layer 1 to the late Pliocene superinterglacials, weak layer 1b to the mid-Pliocene warm period, and weak layer 2 to the Miocene climatic optimum. And then these weak layers are overlain by much coarser grained, lower porosity glaciogenic sediments that would have been deposited when conditions would have looked more like this. So what we think is happening is distinct changes in climate were actually preconditioned the slope to fail at our site. These weaker layers would have been deposited when climates were warmer than today, and these would have been overlain by rapidly deposited, coarser-grained, glacially influenced sediments. And it's the increase in datum content that we find in the weak layers and the rapid deposition of sediment over the top of the weak layers, which would have caused excess pore pressure to develop inside the weak layers, making the slope unstable. Now, we looked at numerical modelling studies from similar sediments in similar settings, and these studies showed that slope failure is unlikely to have occurred without an external trigger. So although these changes in climate actually preconditioned the slope to fail, we need some external trigger to actually generate that sliding. Now, the Eastern Ross Sea, our study area, is tectonically passive. It's not affected by methane gas or gas hydrates, and it's below the depth of impacting icebergs and storm wave influence. We're in over 800 metres water depth here. So we think the trigger most likely influencing our site is glacial-isostatic readjustment, caused by unloading of the retreating ice sheets. So we think what's happening is when the ice sheets are starting to retreat, this uplift is happening, and this is generating earthquakes, which is destabilising these sediments, causing or triggering these submarine landslides. And actually the ages of the submarine landslides correspond to periods following these major climatic shifts. We wanted to look at the tsunamigenic potential of these landslides and whether they pose a risk to southern hemisphere populations. We know that tsunami waves are influenced by water depth, by slope gradient, by landslide volume. So we looked at analogous submarine landslides from similar settings, and these showed that similar sized submarine landslides were able to generate tsunamis. We also found teleconnections between Antarctica and the southern hemisphere, with tsunamis measured arriving from Chile, from Asia, from New Zealand, from seafloor instruments around Antarctica. So what this means is that a tsunami generated in Antarctica is likely to be able to reverse these pathways. So what we find is recurrent slope failure along more than 100 kilometres of the Antarctic margin that occurred since the Neogene. Our submarine landslides occurred above distinct weak layers that correspond to clear, warm climate intervals. And these weak layers are overlain by coarser-grained glaciogenic sediments, which would have increased pore pressure within the weak layers, making the slope unstable. And we need some kind of external trigger to actually generate or trigger these submarine landslides. And we think the most likely trigger at this setting is glacial-isostatic readjustment following ice sheet retreat. Our study has implications for understanding the influence of global climate change on slope instability, on tsunami generation, and the ability to deploy subsea cables in Antarctica, which is a big driver at the moment. I'd also just like to highlight our recent publication if anyone wants to look at this further. And again, I'm happy to answer any questions over email, or you might be able to, or some of my co-authors might be able to answer these. Thank you very much.